I want to talk about thermochemical equations, because all the rest of Chapter 6 is about thermochemical equations. A thermochemical equation is nothing more than a common equation, as we've seen before, accompanied by the delta H of that particular reaction as it's represented by the equation. So if we take 2 moles of water and run it through an electrolysis apparatus and break it down into 2 moles of hydrogen gas and 1 mole of oxygen, the amount of heat change that's required to do this is plus 572 kilojoules per mole. Water, when you hear people saying they're going to be cars driven by hydrogen and they're going to get the hydrogen out of water, this is what you face. To get 2 moles of hydrogen out of 2 moles of water, you have to put in half a megajoule, over half a megajoule. I fearlessly state that it's never going to happen. Okay, if we turn this around, the formation of 2 moles of water from the elements, that's just this equation in reverse, the delta H is the same except for the sign. If we take hydrogen and oxygen to form water, this is the equation for the reaction that drives the main engines of the space shuttle. Okay, not the big engine attached to the side, but the main engines. And equally impressive is the fact that 2 moles of hydrogen and 1 mole of oxygen give over half a megajoule of energy, and this is exothermic. Endothermic and exothermic. So the magnitude of delta H reaction is proportional to the number of moles and for what bonds bonds are being broken and formed. If we took this equation and we form 1 mole of water, half of this, then our delta H would be half of it. Okay? So this would be H2 plus 1/2 O2 goes to H2O. If the H2O comes out in the liquid form, the delta H reaction is half of 572 negative 286. Now, if you notice this, there's a 1/2 here. This is one of the few places where it's okay to have fractional coefficients. Chapter 6, we can use fractional coefficients. Now, thermochemical equations is where we were. And so let me just remind you what a thermochemical equation is by pointing out the features of this thermochemical equation that's on the screen at the moment. Thermochemical equations contain a balanced chemical equation and the statement of the enthalpy change that goes with it. Now, in this case, the reaction is one we were talking about last time, the reaction of hydrogen and oxygen to give water. And notice I picked one here that has a non-whole number coefficient to remind you that this is a place where that's allowed. And the reason that it's allowed is frequently we want to express the heat change that the reaction produces, the enthalpy of reaction, in terms of 1 mole of some product or 1 mole of some reactant. And in order to do that, we may have to use a fractional coefficient here. Okay, so what does this thing say? It says if you take 1 mole of hydrogen and 1/2 mole of oxygen and you combine them in such a way that they make 1 mole of liquid water, if you did that inside a calorimeter, the heat change you would measure would be 286 kilojoules. That's the magnitude of it. Its sign would be negative because we have an exothermic reaction here. Right? So remember last time we talked about the difference between Q and the Q, the heat of a reaction carried out in the calorimeter, and delta H, which is the heat of reaction expressed per mole of reaction. So those are the different things. So in this case, delta H reaction being negative 286 means to form 1 mole of water this way, we will expect to get with it 286 kilojoules of energy. So this becomes a stoichiometric term. make it as simple as possible, it is just another quantitative part of the chemical reaction that we have available. And as such, we can use this information as a conversion factor, and a very important conversion factor, between moles of reactant or product and the delta H of reaction. So we could look at this and say 286 kilojoules of heat is thermochemically or thermodynamically equivalent to 1 mole of hydrogen in this scenario, 1 mole of hydrogen being the amount consumed. Or we could say 286 kilojoules is equivalent to half a mole of dioxygen. That statement is accurate too. Or we could say it is thermochemically equivalent to 1 mole of water. All of those things are true statements, and we can use them to answer various kinds of questions about the heat change in a chemical reaction. So we could use this delta H of reaction to convert between moles of a substance and the equivalent heat change. Let's suppose we wanted to know how much of a particular type of alcohol we would have to burn in a furnace to make a certain quantity of heat. Well, you would take the amount of heat that you wanted and you would work backwards using the balanced chemical equation for the combustion of the alcohol expressed as a thermodynamic equation here to calculate the amount of the alcohol you'd have to use. Here's a simpler one. Working in the opposite direction, how many moles of water could be decomposed by 1 times 10 to the third kilojoules? Well, 10 to the third kilojoules is a megajoule. That's a chunk of energy, a lot of it. How many moles of water could be decomposed by that many kilojoules? Well, we know that this equation up here says that 1 mole of water could be formed. If it were formed this way, it would release 286 kilojoules. So if we turn this equation around so that H2O liquid goes to H2 gas plus 1/2 O2 gas, the delta H for that would be the same in magnitude but opposite in sign because we turned the equation around. So 286 kilojoules is required to decompose 1 mole of water liquid according to this equation. Okay, so what we're going to do here is to start with Q and use Q to calculate moles. Okay? Well, Q is 1.0 times 10 to the third kilojoules. And we're going to multiply that by a factor that will have moles over kilojoules to get rid of the kilojoules and convert this amount of heat into moles. So we would look at this and we would say, okay, the decomposition of 1 mole of water would require a quantity of heat 286 kilojoules. And therefore, the kilojoules will cancel out, and this boils down to 3.5 moles of H2O. So that's the relationship between this amount of heat and the amount of water that could be decomposed. It skips around the question of how you would actually do it. But if there were a means available, maybe this could be electrolysis of the water. It's the only one I can think of at the moment. We should be able, if the process is 100% efficient, which of course it isn't, but if it were, we could decompose 3.5 moles of water. Questions? Okay, so it's a pretty simple quantitative relationship. So I've got another one of these that is phrased in a different way on the next slide. what volume of methane at 25 degrees Celsius and 745 torr must be burned in excess oxygen to yield 1 times 10 to the third kilojoules? Okay. As I think about this, again, I'm going to start with Q, the amount of heat that we're looking for here. And then I'm going to go from Q to moles of CH4 in pretty much the same way I did in the previous example. And then from moles of CH4, we'll go back to chapter 5 and remember PV is equal to nRT. And we could convert from moles, given the information that we need here. The 745 torr is going to have to go to atmospheres, and the 25 degrees is going to have to go to kelvins. And we could then calculate the volume of CH4. So that's the thought process behind it. It just adds a little gas law problem to something similar to what we saw before. So let's work it out. 1.00 times 10 to the third kilojoules. And now here's the balanced chemical equation for this particular reaction. And I think you can see that the coefficient in front of methane here is assumed to be 1. So 1 mole of methane gas is equivalent to 890 kilojoules released. Okay? We're talking about yielding here, which means the same as releasing that much heat. And when I carried this out, I got 1.12 moles of CH4 gas. Okay. Now the second step, if you're comfortable with that one, the second step is to take that many moles and convert it to volume here. So V is equal to nRT over P. So we have to have the right units. And I have converted these. You know how to do that, so I'm not going to spend time going through it again. This is 1.12 moles is N. R is 0.0821 liter atmospheres per mole Kelvin. And 25 degrees Celsius is 298 kelvins. And 745 torr is 0.980 atmospheres. And so once the arithmetic dust has cleared, I ended up with 2.81 liters of CH4 gas as the amount we'd have to use in the combustion to make a megajoule of heat.